Recording, rolling. It's Wednesday, January 7th. So here, guys, look here, So, you guys know we started a brand new topic a couple days ago. So I'm going to do a review with you guys. It'll take a few minutes. Right, so we started learning about torque as one of the examples. So we're in rotational dynamics. Right? Now, by AP's book, this is Unit 5 and Unit 6. And Unit 6 gets into angular momentum, which I'll start getting to by the end of class today. But right, so. So one thing at a time, just got the classes we got. So on AP Classroom, or here we go. Okay. Here's I just opened up Unit 5, Unit 6, or well, they've been open for a few days now. Guys, you guys see the tentative due dates are January 12 and January 13. Right, so that would be as soon as they would be due, and I want to go over those with you guys the following day. If I have to bump those back a day or something, then I could. But right, so those are open for you guys, so you can start reading those questions, start answering those questions. Right. So you guys got 2 AP question assignments. Right, so you guys get so far what we're doing? We're going. Okay. Right. So here, let's do a review from last couple days. So you guys remember turntable physics? You guys remember turntable physics, right? Right. So if I put some objects here, right, these objects can move a certain distance or have a certain speed, but now there's a linear version of each of those and also an angular version. Guys, do these have the same turns per time? Same rotations per the same radians per second, you could say, right? But if I put a speed gate here, they get different linear speeds, right? And the connection between the angular motion and linear motion, you have to very simply multiply by r. Is that right? How fast it's spinning times your location from the center tells you how fast you're moving, right? There's also a distance version of that, like circumference equals 2 pi r, right? And there's also an acceleration version of that, right? So you guys got that. Right, then there's kinematic formulas. So how far does the turntable turn in radians? How fast radians per second? Right. And then there's acceleration. Right. These 3 kinematic formulas are, of course, analogous to the linear versions, right? Distance, speed, velocity, and acceleration. Okay, right. So you guys remember all that? Right. You know what else I wanted to point out to you guys? I had you guys take out your AP formulas the other day, but here we got to mark these up, or at least show you guys what's going on. Right. So you guys remember the left, the formulas on the left column were all from last semester, right? On the right side, these top 3 are your rotational kinematic formulas. Okay. And then these 2 plus this one down here are these formulas that translate from angular to linear type motion. Right. So that's there. Right. And now these 9 in the middle, I can break apart into rotational dynamics of Unit 5 and Unit 6. Okay. So here's Unit 5, relates primarily to rotational inertia and torque, which I'm about to start the review with you guys with that. Right? That's what you guys seen last couple days. Right? And then these 5 formulas down here are related to, well, other things like angular momentum and kinetic energy, which I haven't even got to yet, but I'm working towards. Okay, so there's Unit 5 and Unit 6. Okay, rotational dynamics. Right. So you guys see what those are? Right. Right. So like you guys know I'm making a recording right now, so of course I'm going to post this recording. You get a little closer look, but that's the organization of where we are. Right. You're making some notes right now, though, then just to point this out, below this are oscillation formulas and then fluid dynamics. Right. And yeah, at that point, we'll have covered everything in the class. Back to label got momentum over here. All right. So got those. Got those. Right. Right. So you guys remember we're juggling 3 different types of acceleration. We got linear type acceleration, tangential acceleration. We got the whole turntable can speed up spinning. That's called angular acceleration. Also centripetal. Okay, let's review. Here's what the turntable slowing to a stop looks like. How far it's turned, how fast it's rotating. Negative acceleration. Okay. Rotational analogs. So here's what's going on. Linear motion. Here's the rotational equivalent. Okay, so time is still time in seconds. Let's take right. Instead of how far in meters, now we're saying how far is the turntable turn in radians. Let's say how fast in meters per second. Now it's how fast is it rotating radians per second. Okay. Acceleration. Now we have an alpha for angular acceleration. Okay. You guys remember what takes the place of mass is rotational inertia? So mr squared. Okay. So do you guys remember I passed around those meter sticks the other day? Right. Actually, they're right over there. If you want to get your hands on them or feel them again, or if you're absent, right? The guys where the lab boots were close in didn't have a very small amount of inertia. It was very easy to change the state of motion. But guys, what happens when you slide the masses way out here?
So hard.
Yeah, it's really hard to change the state of motion. There's a lot of inertia, and you can quantify it as mr squared and then add them up. So this mr squared was this mr squared. You guys remember that? Okay. So in a rotational sense, that's going to kind of take the place of what mass used to represent in a linear sense, right? As in, if you go to Newton's second law, F equals ma. Well, now instead of a force, we have a torque, which is R cross F. Right? So we're about to get to that too. That's right, guys remember this torque? Right? Just did live yesterday. Okay, so we're gonna work that. Okay. And if you do have a torque that like a net torque on something, it can cause it to accelerate in an angular sense. Right? So tau equals I alpha takes the place of F equals ma. Okay. So when we eventually start solving these, and these last two lines we haven't even got to yet, but these are related to momentum and angular momentum, and then kinetic energy. Okay, so yeah, just preview. Okay, you guys remember center of mass is just a weighted average, so you can add up mass times location divided by some masses. So if I had a stick stuck through these masses and I want to balance it on my finger, probably close to the big mass, this mass times this location, this mass times this location, add them up. Guys. Divided by the sum of masses, that gives you the average location called center mass. I can balance that on my finger right there. Okay. Right. Or if I threw this to the air and started spinning, it would spin about that point. This is all stuck through it. Let's get through here a little bit. Okay. Right. So, questions so far? Right. So rotation. Okay. So here's rotational inertia for point masses. You can add up point masses to mr squared. Add them up. That's what sigma is. Add them up. Okay. Right. Then I was showing you guys what about rigid objects, because there are some objects that can commonly like roll across the table. Right. AP, by the way, likes the solid cylinder quite a bit. Right. Now you don't have to memorize any of these. AP would give these formulas to you, or I would maybe let you use this table, but you would have to be able to apply these, right? So like, what's the inertia of something rolling across the table? Well, if it's a point or a ring, which all points would be equidistant from this central axis, those are just mr squared. Okay. Okay. But what about solid cylinder? Because solid cylinder, some of these points are located closer in towards the center. So the aggregate effect is going to be less than mr squared, because not all the points are at location R on the edge, somewhere close to the center. Okay. If you do the calculus, it works out to be a half, right? Well, what about all these other objects? Maybe you have a basketball spinning on your finger, it's like 2/3 and so on. Isn't a basketball basically a spherical shell?
Yeah.
Right. So if you run the math, then it's a be 2/3. Right. We're not going to do the math, but that's what it's in the damn. Right. Parallel axis theorem, AP just brought back in the past couple of years. So this is, what if an object is rotating or revolving, not about one of the axes defined on this page. Notice every one of these, there's some axis that I dashed off that's actually rotating with. So like the basketball can be spinning on your finger. That's okay. That's 2/3 mr squared. Right? But what if it's revolving around some axis that's parallel to that axis, like this axis over here instead of this axis here? Hence the parallel axis theorem. Right? So all you do is very simply take the table value and add md squared, where d is the offset distance. Right? So basketball rolling across the floor. Well, spinning on your finger, it's 2/3 mr squared. But rolling across the floor, you guys see it's actually rotating about this point down here. Right? So the offset distance turns out is the radius of the basketball. So I can add mr squared, like md squared, right? And the inertia of rolling across the floor is more like that. Okay, so you guys remember that? Right. Torque, R cross F. So opening a door, turning a nut with a wrench. Right. So this radial arm crossed with this force. Hey guys, this cross right here, it's a special kind of multiplication. It means you're taking these two vectors. These are vectors, right? This offset distance and this force. Right? And you only get to multiply the what components, parallel or perpendicular? Who says parallel? Who says perpendicular? Yeah, there's my winners right there. Right? Because guys, if you push on the wrench like this, does the wrench ever turn the nut?
No.
No, right? But if I push perpendicular, isn't that like maximally effective? Now the whole thing starts to turn, right? But what if I push on some angle? Okay, well now this lever arm is well, it's only f sine theta, right? That's one way to think of it. Okay, so a lot of times the cross product is defined with the sine theta. Okay, where you only get the perpendicular components. Right? Now, if you have a net torque, you can also get a rotational acceleration, angular acceleration. Right, so we're kind of building up to that. This green box right here is like Newton's second law in a rotational sense. This is like F equals ma, but it's tau equals I alpha. All right, let's get through here a little bit. Okay, I know we did a bunch of these on Monday. This is just review. Right here, this one's worth reviewing. Right, equilibrium conditions. Last semester, your equilibrium condition was just forces goes to zero. Guys, focus here. Introduce any Cartesian system along each axis. The forces would still sum to zero, right? What we're bringing in new as of this week is that the torque also has to sum to zero. And this is, okay, now we're getting up closer to your lab yesterday, where you had to use this condition, right? If you are a civil engineer someday, you probably have to solve this in 3 dimensions. So that opens up actually 6 equations you'd have to solve, right? Like the building you're sitting in right now, like every single joint of the building had to be tested, and had to assign some amount of steel and concrete stuff, right? But it all started from this page, right? But a lot of times AP just strips it down to a 2D question, right? Kind of like the lab yesterday. So it's just these conditions right here. You can set up 3 equations, then you can solve them, right? And all right, now we're up to your lab yesterday. The lab was in 2 halves. There was the seesaw half and there was this scaffold half. Well, I can only fit on one on the screen at a time. So let's get the seesaw half. All right. Do you guys remember here? If you pick this pivot point and you sum the torque about it, guys, what if this is balanced? What is the torque sum to? 0, right? But don't forget the forces. The forces also sum to what? 0. Right? Now I drew a couple of forces. I have a weight here, mg, and 3 times that weight over here, 3 mg. Right? But I actually there's one force I did not draw on this page. Guys, which force did I not draw? The normal force. Guys, doesn't the pivot hold up with a normal force right here? Right? And guys, suppose this weighs 10 newtons, and this weighs 30 newtons. What's the upward force from the pivot? 40, because the forces would have to sum to 0. Right? Right. Now, if you switch over and look at torque, that's really what I wrote on this page. Sum of torque goes to 0 newton meters. Right? If I have some weight over here, right, and it's 3 times the distance of this weight, which is 3 times the weight, right? Right. Do you guys see the torque's going to balance? So this over here is causing a counterclockwise torque. This is causing a clockwise torque, but it has to 0 out. You guys see that? Right. And what you guys did yesterday is you said, well, what if I don't know what this weight is, but I can slide it around until it balances? I could solve for this weight. Right? You guys see that? You can solve for the weight if you don't know what it is. Right. So you did that. And the other half of your lab was this scaffold. Now, I'm about to have you guys solve one of these. So everybody has paper out, right? You guys got your notes out?
Yes.
Got the paper and notes?
Yeah.
Right. So same conditions, and the conditions are right here and right here. The forces goes to 0, and the torque also goes to 0. Now, maybe the meter stick itself has some weight, which notice I put the weight of the meter stick right at the center. Is that okay? Can I put the weight of the meter stick at its own center mass? Yeah, that's perfectly fine mathematically to do that. Okay. And then I stack on some weight, let's say right here, for example, and that has a big weight. Okay. And then this is being held up by a couple of spring scales. Now, guys, do the 2 tensions upward have to balance with the 2 weights downward? Yeah, and that's exactly what this says right here. Tension left, tension right, upward, balances with those 2 weights downward. That has to be 0 newtons of force, right? For equilibrium, right? Right. But now we're going to switch over to torque. Now, guys, can I pick any point in the system and the torque also has to sum to 0? Like, if I pick this random point right here, does the torque sum to 0 relative to this point?
Yes.
Yes, right. So when I say torque sums to 0, there's a lot of ways I can set up this equation. But mathematically, there's some good options to pick as the pivot point, right? Same was true on the seesaw, by the way, right? Like you didn't necessarily have to pick this point as the pivot point. Does the torque still sum to 0 about this point right here? Yeah. Does it sum, guys? Does the torque sum to 0 about this point right here? Yeah, if you include like this upward force and you sum all the torque, that would still be true, right? Right. What I like to do a lot of times is to pick one of the locations where one of the forces is acting and sum the torque about that point. Okay. Now, guys, what's the advantage of doing that? Okay. Like here, if I go over here to open the door and I start pressing really hard on the hinges, is that ever going to open the door?
No.
No. So how much torque am I causing by pressing on the hinges? 0 relative to the hinges. Okay. So let's say, for example, what if you did not know either of these tensions? What if you know, okay, I know the meter stick, I know this weight of stick, I'm not supposed to put on 5 newtons, that's what I'm about to give you guys, right? What if you don't know either one of these tensions? Right? Well, if you pick one of these locations as the pivot point, let's say you pick this point right here, then doesn't this left tension 0 out in terms of the torque? Right? And that's what we're about to do right now. So let's do it. Okay. So let's get a meter stick going. Next meter stick. Right. So meter stick's 100 centimeters. Let's put this lab weight right here. Guys, how much does this one weigh? It's 5. It says 500 grams. How many newtons is that approximately? 5 newtons. Right. Let's stack that right here. Stack it right on your stick. Come on, right there. Okay. And let's hold a couple of spring scales at the ends. Spring scale, and this will be at the 0 centimeter mark and at the 100 centimeter mark. Okay. Okay. And this is it will at least reach some tension, like if you're holding them up, and this is all in equilibrium. Okay. So let's say the meter stick weighs approximately 1 newton, which is pretty close to this guy right here. Okay. That was true yesterday, wasn't it? Okay. I'm going to put that at the 50 centimeter mark. So at 50 centimeters, I'll say the weight of the whole meter stick is acting there. Okay. And then this weight right here, I'll put this guy at the 60 centimeter mark. Okay. 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 So I'm showing you guys the actual location. So be saying. Okay. So let's say the weight of the meter stick is like 1 Newton. Okay. Okay. And even though it's distributed over the entire meter stick, it's okay mathematically to treat it at center mass, which would also be the geometric center if it's uniform. Okay. And then over here at the 60 centimeter mark, let's tack on this big old 5 Newton weight. Okay, 5 Newton weight. Okay. And you're holding these 2 spring scales. All right, you guys see that? You guys get the premise? Okay. Is there any questions so far about the setup? Okay. Now, I'll call this tension left side tension left, and this tension on the right side tension right. Which tension do you think is a little bit bigger? The one on the left or the one on the right? The one on the right. Yeah, so I'll draw this one on the right side a little bit bigger, call it tension right, than the one on the left. Tension left. So I got tension left and tension right. Okay? Okay, guys good? Okay. Now, guys, do the 2 tensions up balance these 2 weights down?
Yep.
Yeah, so collectively, the 2 tensions have to add up to how much? 6 newtons. Yeah, 6 newtons up to balance the 6 newtons down. Is that true? So the whole thing is 0? Right. But can you solve for each individual tension with just forces alone, like from last semester? No, you have to you know collectively they add up to 6 newtons. But what are they individually? Right? And that you need torque. You know what? Go ahead. I want to see if you guys can solve it just from that. Right, so because you guys did a lab yesterday that was fairly similar to that. So go ahead, solve for tension left, tension right. I'll give you guys a head start. I'll give you guys a head start, and then I'll start solving it. But some of you guys might be able to figure out the answer maybe even before I started. You're really in the game. What is the left tension and what is the right tension? And the big hint to give you guys is, you guys know the sum of the torque is equal to 0. You're allowed to sum torque about any point you want. And so there might be some mathematically good options to sum the torque about.
Are we using that motion? No, I've been routine all the time.
Okay, so I'm going to start solving this, but since you guys have a head start, see if you guys can beat me to the answer. Right? Actually, when you think you have the answer, then raise your hand and yeah, see if you got it right. Right. So I'm gonna, since I have 2 unknowns, I don't know either of these tensions. I'm gonna pick one of these locations as my quote unquote pivot point. I'll label it pivot. Okay. And since I picked that point on the left, I know that the left tension causes 0 torque about that point. If that's the door hinge and I push on the door hinge, there's no torque, right? Therefore, when I set up a torque equation, I'll only have 1 unknown value and 1 equation and 1 unknown. I can solve that, right? Look at that. Okay. So let's do that. Say, so I'm gonna fit this here. Okay. So sum of torque goes to 0. And that's Newton meters, of course. Oh, hold on. Let me get this phone call. We pause this video. All right, we're back recording, and Ryan and Lily both got it. Yeah, so they're telling me this is 2.5 newtons and this is 3.5 newtons. Now, from a force point of view, those 2.5 and 3.5, that those do add up to 6 newtons total. So that looks plausible, right? All right, so that should be the answer. That's it. So I'm saying the sum of the torque goes to 0. I'm picking this point as my pivot point. Now, relative to this point, I have this radius crossed with this down force. Doesn't the weight of the meter stick itself cause a little bit of clockwise torque? Right, you guys see that? Relative to this point, right? And this weight causes a much bigger clockwise torque for 2 reasons. One is it's more weight, but also it's further away from this pivot point. So for both those reasons, that'd be more torque. Okay, so that's the torque. Okay. And then what's holding it in check is this tension on the right side. It's holding back, providing a torque counterclockwise. You see that? Okay. So 2 clockwise and 1 counterclockwise. So relative to this point. So here's R cross F, and then this R cross this F. Okay. You see that? Okay. That's exactly what I said. Also, while I'm having this diagram up, do you guys see that each radial size is each radial distance is horizontal, and each force is exactly vertical, right? Which means that the angle between each one of those is what? 90 degrees. It's 90 degrees here, 90 degrees here, and 90 degrees here. Right? And what sine of 90 degrees would be 1? So I can just multiply the r and the f together. So for each one of those. Okay. So go up here. So I got, I know torque, of course, is r cross f. Right? But these are already all perpendicular to each other, so I can just multiply. Right? Right. So I need sum of torque to be here at 50 centimeters. 50 centimeters. If you did meters, you 0.5, but you'll still get the same correct answer. Right. There's a 1 Newton weight, which of course the weight of the meter ship itself. Right. Now, do you guys see how that's clockwise? Right. I could call it down negative and make it a negative force. Right. Usually clockwise is considered the negative direction. Right. Right. And then plus, and then there's at 60 centimeters, I have this 5 Newton weight, and since it's down, I'll call it negative 5 Newtons. Okay. And then plus, and then all the way at the other end of the meter stick, which is 100 centimeters out, okay, I have tension right, which at the beginning I don't know what that is, but I do know this all has to sum to 0 Newton meters. Okay, I guess that. So I have clockwise, clockwise, counterclockwise has to all zero out. Okay. Okay. All right. Then to do the algebra here, well, maybe we'll throw in the middle step. So 50 times 1 plus 60 times 5, right? This all comes out to...
Isn't it 50 times negative 1?
Yeah, and then negative, yeah. Okay. Newton meters plus 100, oh, sorry, that's Newton centimeters, isn't it? Right, 100 centimeters, and tension right goes to 0. Newton meters, Newton centimeters, whatever. Okay, add this over, divide by 100. I'm getting tension on the right side is 3.5 newtons. Yeah, has to be 3.5 newtons. Okay. Right. Then to get the tension on the left side, well, there's a few different ways to do it. Now that you know the tension on the right side. Okay. So
don't you know it has to add up to 6? So you just subtract them, right?
Yeah, you can totally do that. You could say the sum of forces in the y direction goes to 0 newtons. Therefore, all the forces up, all the forces down. Okay. So what do I do here? Tension on the right side, which we just found, is 3.5 newtons, plus tension on the left side, which let's say we're solving for, right? And then minus 1 Newton and 5 newtons. So minus 1 Newton, minus 5 newtons. That all has to zero out. And then you can get tension on the left side is 2.5 newtons. Yeah, that's a good way to do it. It's probably what I would do. Right, something like that. Okay. Guys, could you do this instead? Could you have started this by picking maybe this point on the far right as the pivot point? Right. And you could have solved for torque left first. Use it. The tension on the left side using torque. Right. And it would have given you 2.5 newtons. Okay. You can do that with
too. Like pivot point in the middle. Would that have been pivot?
Yeah. Okay. Now, guys, what if you pick the pivot point right in the middle?
And you just wouldn't use that force in the equation.
Yeah, I wouldn't start doing that because there would be 2 unknowns. Like both of these tensions would show up as unknowns in a single equation, so you couldn't solve it right away. Right? What you could do is you could pick the middle point as the pivot point after you solve the tension on the right side, right? And then you could still use a separate torque equation, and you could get the tension on the left side. It would still be 2.5 newtons. Okay, right? Any questions about that? Okay, that's it. All right. All right. So. Okay. Right. Any questions about the scaffold? Right, because that's a really classic question, really classic setup. Right, so that's where you want to. Right. So next time you see this, it could be another question I give you, or a textbook question, or a quiz question, or an AP question. Because this one shows up all the time. Right. The roadmap is set up the torque goes to 0. Pick a pivot point that's at one of the unknown forces, and you can solve for the other force. Right? And then after that, a lot of times it's convenient to set up a force equilibrium and solve for the other force. Okay. Boom, boom, boom. Just like that. All right. So got that. All right. So lab table you guys had yesterday looked fairly similar to this. Well, that was one half of the lab, and this was the other half of the lab. So you had a seesaw and a scaffold. Right. Right, here's another classic question that I see show up all over the place. Back when I was in high school and college, and then AP questions, this one shows up all the time too. Right? It's a ladder rests against a wall, and you guys see where it says a frictionless wall? So if the ladder set rests against the wall, notice how I didn't draw any friction between the ladder and the wall. Now there's friction with the floor, just not the wall, right? Because it simplifies a bit, so you can actually solve this. Okay? Right, so if you solve something like this, then I'm thinking these conditions right here. So at rest, it's a type of equilibrium. So the forces have to sum to zero. That'd be true horizontally and vertically, right? But you also need this condition here. The torque goes to zero to be able to solve any kind of question you get, right? One of the classic questions is, what's the minimum necessary coefficient of friction between the ladder and the floor, right? Because there have to be some friction here. So there's some minimum necessary friction. Like, guys, do you think if I put some wax paper, down here and get rid of most of the friction, do you think it's really hard to get the ladder to stay at rest? It just wants to slide down like this, right? Right. So there's some minimum necessary coefficient of friction. Here, let's solve one of these two. But I'll show you guys how to solve it first, and then throw some numbers at you guys. Okay. So for the diagram, now I call this a free body diagram. They might call this a force diagram because here's one difference between what you're looking at right now versus last semester. Do you guys see how the forces I'm actually locating at specific locations now? Right? Because these forces at different locations on an object might start to cause individual torques. Now, of course, the sum of the torque goes to zero. Right? But now you're thinking of forces at different locations. So if you see force diagram, consider it like a subcategory of free body diagram, something like that. Right? But what are the forces involved? Well, the ladder has a weight, and just like with the meter stick a few minutes ago, I'm putting the weight as though it's a single location at the center of the ladder. Okay. Maybe the ladder is uniform. Okay. There's a normal force on the floor to hold it up. Ooh, guys, if you compare these two forces, which one's bigger, or are they the same size? Same size, and that's this condition right here. The y direction forces have to go to zero. Right? So the floor pushes up on the ladder as much as the ladder is pulled down. Right? And now that's strictly only true if there's no friction with the wall, but there is no friction with the wall. Right? Right? So those are vertical forces. But what about horizontal? Now the wall is pushing the ladder to the left, but the friction is holding the ladder back in check to the right. And those also zero out, and that's your horizontal force condition right here. Okay? You guys good? Okay. All right. And then the third condition is the torque goes to zero. So if I give you guys maybe a length of the ladder and the weight of the ladder, what if you can figure out coefficient of friction? Okay. Now, what does this equation say down here? Here's a torque setup. So it looks like what I did. Can you guys see? Here, maybe you can figure out a reason or look at this equation and figure it out. Which point did I pick as the pivot point to be able to set up this equation in the screen box?
The base of the ladder, right?
Yeah, how about the base of the ladder? Guys, doesn't that look like a really good option for a pivot point? Because two forces are at that location. So don't they each cause zero torque relative to that point? Right? Like pressing on door hinges of door. Right? Which means that if you set up a torque equation, you'll only get two torques from these two forces. I think that's what I have set up here. So mg is the weight of the ladder. Do you guys see if the length of the ladder is L? That this would be at L over 2. Do you guys see that? L over 2. Right? But guys, what's the lever arm? Do you guys see the lever arm from this point to the weight is this lever arm right here? Do you guys see that? Right? Now here, I'm going to cover this up. So when I'm covering up right here in my left hand, does this say sine theta or cosine theta? Cosine? Yeah. You guys see, because it's adjacent to that theta, right? So like if I define the other angle, if I define the complementary angle, it can be sine of this alpha up here, but it's cosine of this theta, right? Right, and then here, I'll cover up something else here. Okay. Because there's another force causing a different torque. So at the full length of the ladder, from this pivot point to the wall, right, there's a normal force from the wall. Normal force, of course, pushes perpendicular to the surface, normalist, right? But now this is your lever arm, right? So guys, what I'm covering up with my left hand right now, does it say sine or cosine of this theta? It's got to be sine, because see how that's opposite of that theta? You guys see that? Right. So that's the basic setup for the scenario. And now I just have two individual torques, and they have to zero each other out. This one says, let's go clockwise. This one says, no, hold it and check counterclockwise, and they zero out. Okay? Is that one? All right, do you guys think you can solve one of these? Oh, yeah. All right, let's do one of these. All right, so ladder time. All right, so what is the minimum coefficient of static friction? mu sub s, right, between the ladder and the floor. Okay. Yeah, we're gonna call the wall frictionless. Okay, let's just go ladder to the floor. Okay. And so I set up a ladder here. Here's your ladder.
Between the ladder and the wall.
No, the ladder and the floor. Okay. There's zero friction with the wall. There is zero friction with the wall. That's a common simplification to make with this particular question. Okay, so there's the ladder, resting against, well, the wall on the side and the floor on the bottom. Okay. I need to give you guys some numbers. So let's say the length of the ladder is like 5 meters. Let's say that the weight of the ladder. Here, I'll draw you guys a weight vector. But let's say the weight of the ladder is 20 newtons. And let's say that this angle with the floor, call it theta, is like how about 25 degrees?
ASU.
Or that doesn't make sense. Hold on, let me get rid of that. That doesn't make any sense at all. Let's go 75 degrees. Let's go 75. Get rid of that. 75 degrees. There we go. That looks better. Okay. All right. Okay. So you guys are trying to find what's the coefficient of friction between the ladder and the floor. Okay. Yeah, you actually right there. That's all you need. Okay, that's all you need. Okay. Now I'll help you guys out a little bit. Let's finish the rest of this diagram. Because I know there's a well, because if the Earth is pulling the ladder down, then what is holding the ladder up?
Normal.
Yeah, the normal force from the floor. Right? And is the normal force how many newtons would this be?
20.
20. Because it's the only other vertical force, so it has to balance this one. So this is the normal force from the floor. Okay. Okay. Now notice those forces are at different locations on the ladder. So if those were the only forces, if you're out in the middle of space, you just put those two forces, maybe had a string like that. When the ladders start rotating, right? But it's not. It's at rest because there's a couple forces I haven't drawn. I need what's another force I need? Yeah, friction force, and that's from the floor to the ladder. Okay, so I'll call that F sub FR. Okay, and what other force do I need? Yeah, the normal force from the wall on the ladder. Just gotta go right here. F normal wall. Okay, so there's your setup. The three numbers I gave you the full length of the ladder is 5 meters. I gave you the weight of the ladder is 20 newtons, and I gave you this angle of the floor is 75 degrees. Okay? There's enough information there. You can solve for the coefficient of friction with the floor. Okay? So just like before, I'll give you guys a head start. Right. So go ahead and start solving it. And I'll jump in about a minute and see if you guys beat me to the answer. Yeah, last time you guys beat me to the answer.
Okay, and so mg times over 2 is going to do sine theta as well. Well, here's it was from the wall over tau sine theta, right? Yeah. Yeah. And where's that from? Sine theta. Plus normal for the wall times the limit of sine is 5. Here's what I'm yeah, this is the way of the ladder. This is the cosine for it is this portrait. And then plus the other
So I'll start solving it up here. Okay. And yes, it's still if you guys can beat me to the answer though. Okay. So again, play off this formula that I have set up already. It just goes like this. Okay. So mg at L over 2 and then cosine theta, right, because this lever arm. Okay. So I'll do that. So I'll say, well, see if can I fit this way? Yeah, that kind of fits, I think. So the guiding principle is sum of torque goes to 0, and the unit is Newton meter. Okay, 0 to 2. So there's two individual torques. And do you guys see too? I'm gonna pick this point right here as the pivot point.
Yeah.
Pivot. Okay. And I'm gonna sum the torque about this point. Okay. Okay, so that's torque, of course, is R cross F. Okay. Yeah, so here's your lever arm as it applies to the weight. Okay. And this would be L over 2 and then cosine theta. So L over 2 cosine theta, that takes the place of that radial arm. Okay. And then the weight is acting at that point. Okay. Now, you guys see how that's clockwise? So also have a negative somewhere there. You can have the weight negative where I'll just factor out a negative. Okay. And then plus, and there's a counterclockwise torque from this force up here. Now that's at L sine theta, which this is the lever arm right here. You guys see I'm marking out this lever arm up here?
Yeah.
Okay. So that's L sine theta. Okay. And then the force is normal force from the wall. Right, so like that. Right. And all that has to sum to 0. And the unit is Newton meter, 0 Newton meter. Okay. You guys care with the equation setup?
Not yet, not yet.
Okay. Now, since I gave you guys some numbers, I'll go ahead and plug the numbers in. Okay. So the length was 5 meters. The angle was 75 degrees. Okay. And then the full weight of the ladder was 20 newtons. Okay. And then here I have 5 meters sine 75 degrees. And then force normal wall. This whole thing goes to 0. Okay. Okay. So I have one equation and I plugged in all the given values and see how I have one unknown value. Okay. Now it wasn't the target question. The target question is about coefficient of friction. And we're working towards getting that one step at a time. Okay. But I could solve for this, right? You do that? Okay. So let me do skip. I'm going to skip some algebra and just plug this in my calculator. So it's 5 over 2 times cosine 75, and then times 20. Right? And then divide by, you guys solve this too, make sure that I'm getting this right. I'm getting that the normal force from the wall, normal force wall, is equal to, does that look about right? 2.68
I was right.
newtons. Are you guys getting that too? About 2.68 newtons? Okay. I'm going to double check my math while you guys are double checking.
I'll use my original equation.
2.5. Okay, so 75 times 20.
Yeah, I'll do the square root of half. 20 times 5.
4. 5 times sine 75. Yeah. Okay. So here's the normal force of the wall. Oh yeah.
How did you get the first negative L over 2 cosine theta, etc.? How did you get that?
This right here.
Yeah.
Okay. Right. So I summed the torque about this point right here. This point right here. Okay. Now, relative to this point, these two forces cause 0 torque. So I can just throw them out of the torque equation. Right. So this times 0, this times 0, whatever. Just ignore this. Okay. Okay. The weight of the ladder is trying to make the whole ladder rotate clockwise. You see clockwise? Right. But the lever arm is right here. Here's your lever arm for the weight. Right?
Yeah.
Right. So from here to here is L over 2, because the full length of the ladder is L, right? So from here to here is L over 2. Right? Okay. But playing off this angle theta, do you guys see a nice right triangle right here? This is L over 2 cosine theta. And that is right there.
Can you show me how you put it in the calculator? Because I did it and I got it.
Yeah, I'll do that too. Okay. Right. And then the other force that's causing a torque is the normal force from the wall, which is what we're solving for, is one of our middle steps. Right. Now that's acting at the full length of the ladder, but it's pushing not perpendicular to the ladder, but perpendicular to the wall. So the lever arm is this height of the wall right here. You guys see the height of the wall is actually L times sine theta, right? Right, and that is that lever arm right there.
So basically,
Okay, so clockwise and counterclockwise have to 0 out, right? And that's where I got to here. Okay, now how do you plug this in a calculator to get this? Okay, so I can plug all this in my calculator and then add this over. Right, so type 5 over 2. Right, so you're typing this 5 over 2. And then I got a cosine of 75 degrees. whoops, cosine 75, close parenthesis, essentially. Make sure your calculator is, of course, in degrees. Guys, all this right here, I got about 12.9 Newton meters. You guys get that? About 12.9 Newton meters? Okay. Now, if I add that over, I can divide by this without leaving the wall force. Okay. So I'm going to divide by, and then open parenthesis because there's multiple things here.
Wait, why is that division? I thought that was a division.
Okay, because, right, guys, what we're doing is we're taking all this, which is 12.94 Newton meters. Now this is negative, so I'm going to add this over to this side. It's a 12.94 Newton meters. Then I'm going to divide by this coefficient, and that will leave me with the wall force. So divide by 5 meters times sine 75 degrees. Okay. Now your calculator, you have to put that all in parentheses. Put that all in parentheses, right? Because you're dividing by multiple things here. Okay. Which I'm doing right here. Divide by open parentheses 5 sine 75 degrees. Okay. And that gives me this 2.68 newtons. Okay. Right, so just a little algebra there. Right. Now, guys, once I know the normal force from the wall, let's go back to the original picture. Okay. Because if this is 2.68 Newton, then what else do you know? The friction force, which has to be equal to what? Also 2.68 newtons, just the other way. Because these two have to zero out horizontally. Is that true?
Yeah.
Because it's equilibrium, force equilibrium. Right? So okay, so now I know the magnitude of the friction force. And since the question was coefficient of friction, then we're almost ready to answer that. Okay. Guys, coefficient of friction is, well, you can think of it as a ratio between what force and what force? Yeah, the friction force compared to the normal force. Right? Okay. And we're looking for the minimum necessary coefficient of static friction. Like if it was any less, the ladder would break friction, slide down. Right? So it's like barely hanging on. Okay. So the minimum necessary. Okay. And for the friction force, well, you said it has to be equal to this other force we just found, which is 2.68 newtons. Is that true? Okay. And guys, what does this normal force from the floor have to be equal to? Yeah, the weight of the ladder. Because that's force equilibrium in the vertical. That's your 20 newtons. Right?
I thought the 2.68 newtons was the normal.
Yeah, it's the normal force from the wall. Guys, there's two different normal forces here. There's the normal force from the
Why
wall.
did you put it under the force of friction? So, like in the equation.
Okay, guys, because what is the sum of forces in the x direction equal to? 0 newtons for equilibrium. Okay. And there's two individual forces. There's a normal force from the wall pushing left, and there's the friction force pushing to the right. So they have to be the same magnitude as each other. Okay, because they subtract out and go to 0, right? Okay. So in the math, we found the normal force on the wall, but that must also be equal to this friction force. And that's what this is. Okay. And then the normal force from the floor, this is from the floor, right? Which has to match the weight of the ladder. That's right there. Okay.
All right.
Okay. So now we're about to put this all together and get the minimum necessary coefficient. So US minimum is equal to what's 2.68 over 20. Look at 0.134. Okay. Okay. Does that look pretty well reasonable, like in line with reasonable coefficient of friction that you guys could eat? Right? That's a relatively small coefficient of friction, like 0.13. Like normally you see like 0.2, 0.3, 0.4, somewhere in there. Right? But that makes sense because we're looking for a minimum necessary with this situation. All right, here guys, we still got a couple minutes. Okay, so at least want to show you this. Well, let's do this next one. Okay. All right, so guys, here's another classic question. This is the scaffold question with a twist to it, which is we're going to take this right cable and put it at an angle. You guys see that? All right. Classic question here. So guys, just give a good look at this. Last couple minutes of class. So the forces going on is this beam is allowed to pivot about this point. You guys see like a joint right here where I can pivot? You guys see where I can pivot?
Yeah.
Is that right? So maybe the beam has uniform weight, so I'm going to put its weight also its geometric center. So mg, it's pulling straight down. And if you let it go, if this cable wasn't here, guys, wouldn't this beam want to rotate clockwise or just fall straight down?
Yeah.
So we're going to put this cable at some angle to lock it in place. And usually the question is related to what's the tension in the cable. That's usually the classic question. Okay? And here's the setup. So the force is sum to 0 in each direction. the torque sums to 0. Okay. Right. And here's the other forces. So I got the weight down, I got the tension in the cable flowing along the direction of the cable, of course. Okay. Now at the joint's actually playing well, I actually drew the two components of the force, right? The joint's both pushing the bar to the right, but it's also holding it up. So I just drew the components as though they're individual forces. But guys, if you sum the torque about this point, then aren't these forces irrelevant to that equation? Right? I think it's what you did down here. So at L over 2, I have mg. There it is. L over 2, you have mg. That's that torque clockwise. Then at the full length, there's the cable pulling, full length of the cable. And based on this angle, if you think about it, it has to be sine theta. Hey guys, what if the cable is pulling straight up? What would this angle be? 90 degrees, right? And sine of 90 degrees would be 1 to get the full effect. Right, anyway, that's the setup. So that's our pause point. You guys have a good day.